on the upper left of this covariance matrix is the variance of the first variable, which is just its correlation with itself. So you should know intuitively that it should be 1, right? And same with the variances on the lower right of this variance covariance matrix, which is just the correlation between x2, second variable, and itself. So what should be of our utmost interest should be those on the off-diagonal element. For example, this one, sigma sub 2. That's the covariance between the first variable and the second variable. And then for sigma sub to 1, that's also the covariance between the second variable, depending on your perspective. Right. The second variable and the first variable. So if two variables are uncorrelated, then you know that, okay, so their covariance is just 0. Right? And that actually put us in perfect order. Meaning that, okay, we only need to watch out of this, right? And then they are perfectly estimable because they are just 1. Those diagonal elements are just 1, right? Because that's the correlation between you and yourself. It's just 1, right? And then in that perfect order, everything except with the element in the diagonal matrix are uncorrelated. They're just 0, and then they are perfectly estimable. But however, under most circumstances, they are not. So we have to incorporate that into effect, and that this goes all the way back to what I just mentioned, like 10 minutes ago. I'm saying that, so you might be asking, so is that good that we keep adding variable into the model? No, I said it's not necessarily the case because those redundant variables may have to be correlated with those important explanatory variables that go into the model. And then if you keep adding that into your model specification, then you're going to inflate the covariance term, right? And that will reduce the predicted power of your model by inflating the variance covariance nature. Right? Okay, so we take 5 minutes break, and we have a really all day. And after that, we'll get back and finish our linear regression.
He's the master of the data science. He's the boss of he's the boss. So he works in academia. Oh, really? He's also research. And then like come here to so you get pretty good experience compared to me. Yeah. questions pretending they're reaching.
Did you see But the Russians have a good record. The Chinese don't have.
Yeah. But I mean, very hard. China they got like pepper sauce.
课文还没看过。还有拿课文，然后900多页那个。
Yeah, they got a lot. That's So I don't know which one is better. Did you saw the Russians they just hiding because they are lack of logistics support. They just like crowding fire. They do not eat the Yeah, I saw that much in the It's like counted. But I'm not sure if Russian state, the name didn't come out and stuff. But they're like on I'm not sure will anybody Yeah, but I mean Western country, we don't need to fight with them. I think maybe this kind of Here we go. Yeah, the cold war is sold in nuclear to UK. I remember these days. I remember some of these kind of stations inside Ukraine. They like do nuclear like the news. The US is like
Alright, so the class will soon.
We will find out where they have it.
Alright, so for this whole lecture, we're going to show you how our estimator, we care many about the beta term, even though in later part of this semester, there was, for example, other aspect of the model, for example, like the beta term, how do we do the inconsistent estimate resulting from the wrongly estimated error. So for now, we care mostly about the degree of association between the explanatory variable and outcome variable of interest. So here we're going to focus on beta coefficient. So suppose we want to get an estimate of the beta that best captures the relationship between any two variables. Right. So for now, we're just focusing on the univariate distribution. Focus on the bivariate relationship between two variables. One is a variable and outcome variable. So, of course, we want our estimate to capture as many data points in a relationship between two variables, x and y. So, one intuitive way to do that is to try to conceptualize a metric, a measure or something that, just like you try to project a line onto a space spanned by some x, your explanatory variable. And then your objective is to minimize the error or some distance that you feel to capture between the actual value, a y variable, and your predicted variable. Which we usually use y hat to represent this. And y hat is a function of our explanatory variable, we call it the error term. And your differences is the error term. So you might want to go switch to our slide. I'll show you put down a show dropout filter and also put down an NTU cool. Right. And you can actually imagine this tab as trying to capture the shadow of a hovering object y. Right, so that one was right, so shadow hunter. I don't know. I heard a student say that's actually a drama. I'm not sure it's on that class or the other one, but anyway, horrible acting. Suppose your task is to try to capture the shadow of an actual object that's seen here. So in a multi-dimensional space spanned by some explanatory variable x, multiple x, then there is a y hovering about. Actually casts a shadow on the graph of x. And what our task is to project a line that can eventually reach y. Right? So that's what we do. So that, because it's not vertical, so the beta cannot fully capture the relationship between x and y, right? And beta, so we just trying to referring back to this geometry you probably learned in high school. Beta is actually the slope, right? Does that make sense? It's a slope. You try to project a line from a surface spanned by some explanatory variable x onto the y, which is hovering about. And you try to minimize your error, minimize the distance between your projection and the actual object. So here is y hat. Right. Or we simply replace x with y hat. And the differences is called epsilon, or error term. They want to minimize the epsilon to the extent possible. So how can we do that? And that's pretty much like the namesake for ordinary least square model. Say that the least square, meaning that we try to get smallest square error to the extent possible. Sure. The best case scenario would be is exactly 0, right? So simply square is a vector of our error term. So you might notice that there is a prime here, there's a prime here. Because that means this part is a transpose of this term. You've seen that previously. Here. Okay. So when I say transpose, means that I simply swap each row element in the vector or in the matrix with its corresponding column element. So a good estimator from the ordinary discrete model should have minimum variance, but the square error here, the error can square the error. So the best case scenario will be there 0. And in that case, well, if the error term is 0, then that implies or predicted value resulting from our design matrix times the coefficient, the beta term, y hat equal exactly the actual value. We can actually show this. Then by arbitrary extension, suppose you open this, right? This is a high school class. Suppose you didn't forget. Okay. And then we differentiate this with respect to the beta. Right? Now we want to get optimal value of beta, so simply do the maximization argument. If I had put R max in my note. Right? So this term, the first term doesn't contain beta, so we can take them out. Right? And for this part, we know that we differentiate this with respect to beta. This would get, oh, right. Before that, we need to set this to 0. And then you put this on the left-hand side, this equation. Right. And then we solve for phi. So it can be done, but simply rearrange it. And take that out. Now we get it. And you might also further notice that, and actually cross this out. This together can be tested out, right? And y over x is just the slope, right? So that's a bit. So it's simply the same as I showed you here in the note. Right? And also it follows that the constant term, or the beta 0, is just the actual value minus the sign matrix, your respondent variable, minus corresponding beta coefficient. So if it happens that x1 is 0, or it doesn't have any statistical correlation with the y, the actual value, that means y, if it perfectly explained by the constant term. Right? We can also use the same arrangement to prove that the error term is most efficient if, or the error term, and so under the condition that error term equals 0, and then which would make beta the most efficient and best linear estimator for the actual value. So suppose that predicted value of our the actual object, the actual value, can be obtained by exponential variable intra and its corresponding coefficient, right? That y hat. Then the error term is simply differences between the actual value and the predicted value. So here's our friend, the covariance term. So, well, if if x, the responder variable, is uncorrelated with the error, I mean that your responder variable can perfectly predict the outcome variable of interest, such that your predicted value equal exactly your actual value, so that the error term is 0. That implies those terms, even though you want to explain that through algebraic extension, as I showed before, are both 0. Okay. And then we got a very fast and very efficient estimate. If, on the other hand, there's some correlation, then you should probably do something else. For example, like adding new variable into the model or adjust its measurement. So why is this so? So we can actually show this. I think I probably don't need to write anything here. So suppose the beta is expressed this way. The variance in x is covariance with the y, outcome variable interest, which by substitution, you can substitute the expression for the actual value into here, into this original position, which is just exponent variable times this coefficient plus some estimable variable, estimable error. Okay. So you can then decompose it by the first part and the error part, right? So we want to show you here why this must be so in order to make the beta the most efficient and best linear estimator for y. So this part is extremely simple because the correlation between x and x times beta is just beta, right? It's just beta. This part is the same. I mean, the only thing there is this part. It's just beta, so we can take that out. Right? So here is the only thing that's left here is to measure the covariance between x and some random error. So in order to make the beta the best linear predictor for what? That implies this term must be 0. Right? So that beta equal beta, and this part on the condition that the error turns 0. So that this part is reduced to error. No, it's reduced to 0. We can actually show this here. Remember that the previous slide said that in order to beta to be the most efficient, there's a best estimated for the actual value. This part must be 0. The error must be 0. And then beta must be its predicted value. So here. We also try to minimize the predicted value and its actual value using the least square method. And we know that since we previously get that beta is equal to so we can simply substitute that into the model. Right? And we also know that y can be represented by your exposure variable interact times is coefficient plus linear error. So that's why I put this here. And here, you know that you can cancel these two guys out, right? So that beta we can determine this on. We can put it in the first group. This become this part. And then look at how you can also shift beta to the left hand side of this equation. So that we actually derive a minimization condition for the beta. So if those two parts, if they are 0, meaning that you get the best estimate because you're exactly equal to the actual term equal exactly to your predicted value. And this one must also be 0. Then we can substitute this condition, right, back to this part. Right? So simply square that, right? And you will get this. And note that you can also cancel them out, so that you're only left with this term and the error. And since the error can be represented by sigma just standard error. We'll talk more about standard error in just 10 minutes. Right. And this part is enclosed inside an expectation function. The E means expectation. Okay, so we are only left with this one. So what should we do? See that? Okay, so they are exactly 1. So that we have to mu because you have just seen them before. It's here. Meaning that if the error term associated with the explanatory variable that I put into the model, they are uncorrelated with each other. So what's left is some estimable error. Consists of the correlation between each variable and itself. It just is square variance, which is just 1. Right? Your variance versus itself is just 1. That makes sense. So that in identity matrix like this, So I didn't measure like this. It's just sigma squared, your estimable variance, because each sigma is a standard error. This square is a variance times by a matrix. So in the perfect world, your linear estimator, you'll get the best linear estimation of the actual value if you minimize the error to the extent that there's zero. They only that with a diagonal matrix. You need to tackle the variance between all these one variable and itself, which is just one. Question here? So this picture, where actually you can see the 3D plot is cool, and you can replicate that in our archive page. Actually, a supply will here. So you can really try to think, I just want to use it for pedagogical purposes. You think of estimating, say, try to capture the amount of variation in a dependent variable in Y by projecting a multidimensional plane onto a space spanned by some X, your explanatory variable. So that this hyperplane, the surface, minimize the average distance at all points. Because you might assume that, for example, you're trying to predict people's height. Some people's height and some people's human height are below population average, some are above population average. So try to get the reliable estimate, a reasonable estimate of the nation's population average height. We just project a plane that minimizes the average distance for all data points from the mean of the data, population mean of the data. And that's why the Oliver's model does. Okay. So now we get to another concept of distance. So the distance is actually the deviation of the predicted value. Here's your predicted value. From the actual value of the data point, the ice data point. So simply average this value for across all the data point to get a least square error. And also know that, so there's a like minus 2 in the denominator. So you might ask, so what does that mean? That means, well, since you have one dependent variable, and also you use one independent variable, one explanatory variable to explain the movement in the dependent variable, so that you lost 2 degrees of freedom in the estimation of the statistic. So that's why we need the minus 2. So if you try to use like k explanatory variable to explain the variation in the dependent variable, then you lost. So your degree of freedom will be the total number of observation minus k number of explanatory variable that you use minus 1 in the dependent variable. Right. Also, you can also get a sense of dispersion of the data from the average, or from the mean of the population estimate. That would be Rubin squared, or called INSE. Simply square this term. But you said, no, of course, I think that some of you are freshmen or sophomore. I first learned mathematical statistics my sophomore year. And but before that, we only know some elementary knowledge about, say, distribution. And we haven't tried to use explanatory variable to explain the variation in the dependent variable. And back then, what we're talking about are about like variance, standard error, SD. But now you just mentioned the standard deviation. But now you just mentioned standard error. So what does that mean? It's very confusing, right? But so there's major differences between this. So when you talk about variance, it actually means the variation in the observed value. Because estimation is not conditional on any explanatory variable. You're not trying to explain the variation in data. You just simply do a pure description of the dispersion of the data, right? So that you also see that the degree of freedom is just -1 because you only use the actual value, the observed value, to explain its own dispersion. Okay. So the corresponding concept that you can map to the RMSE Ruby square is called standard deviation. Know that it differs from standard error, standard deviation. And so the denominator is the degree of freedom in the denominator is also -1 because you only those one repeated in the estimation. But here's a short explanation. Also note that standard error is actually the how spread out the group data is. So the larger this value take, the more spread out of this data from the mean value. Okay. Another corresponding concept called distribution. It means that the distribution of variable is simply a summary, or we want to say a description of how the relative frequency that each possible outcome can take along the range of value for that particular variable. And as we know it, more extreme outcomes occur less frequently, for example, like human height, because rarely do you encounter someone is taller than 68, really like 200 centimeters, right? But where in actuality, most outcomes occur around the mean of the distribution. Right? Makes sense? Yep. And by normal distribution, around 68% of the sample fall within one standard deviation of the data, or 95 fall within two standard deviation, 99.7 fall within three standard deviation. Essentially capture pretty much all the data. And there's probably some graph that you can find on the back page of all statistical textbook. So suppose you want to draw a data point for a normally distributed data. The probability that a particular value will occur is described by the so-called probability density function. As I said, most values of the variable occur around the mean of the data, meaning that the density mass around the mean of the data is probably the highest. So suppose you simply do a random draw near the mean of the data. You probably grasp most of the data. Right? You move toward the left or the right most extreme of the data. You're probably only grasp just only a few observations. Meaning that the probability that the number of observations you will get with a random draw is the highest around this mean. The probability density function, the PDF, is probably one of the highest around the mean. But as you move to the left or the right most extreme of that value, it should decrease. And for corresponding concepts called cumulative distribution function, know that even though it's called PDF, it's one called CDF, they actually refer to different D, right? First one is the density, the sequence distribution. Meaning that the cumulative probability that you will find the value smaller than the particular value is described by cumulative probability function. So for example, suppose I would say, trying to figure out the probability of running to someone who stands taller than 6'8", 200 centimeters. So suppose the probability is like the cumulative probability smaller than right, means people are shorter than this extreme tallness. So the CDF would probably be 99.9, I think. And you say, okay, that makes sense. So, can there be any possible real-world application? Yes. But before that, we need to get down to some measurement issues. Because we want to measure how, I want to get a more objective measure of, say, the probability of observing this extreme value in normal distribution. Two related concepts, though. First is t-value, and the second one is z-score. They correspond to different situations. So whenever you're using a exponential variable to capture the major variation in the dependent variable, okay, so you include one x right into your equation, then you can measure how the estimated simple mean differ from the population mean in the data. So you should represent it, so you should divide their differences by standard error. And with error here, meaning that you include an exponential variable into your equation. So the larger the t, the more extreme is your estimated value. And when you put it on the PDF and CDF terms, meaning that the probability that you will encounter a situation as extreme as this, meaning that you will encounter something larger than that, is extremely small. But it turned out that okay, you get this extreme measure, meaning that okay, so it's very unlikely that you encounter a chance, meaning that there's definitely some positive or negative association behind this. We'll definitely get more on this later. But related concept called z-score. You probably all know this before. The standardizing score, meaning that standardizing the score deviation from the standard deviation of the data, meaning that I use SD here. That means you did not include an exponential variable into the estimation. But it can be a good thing because t-value corresponds to itself, right? Is related to a particular measure for a particular variable, but it's not comparable across different exponential variables. So you use like two exponential variables in that, and then the t-value that you get for the first exponential variable is not comparable to the t-value you get for the second exponential variable. For z-score can be because it essentially standardized score on the same scale and dividing score deviation by the standard deviation of the data. So we should be able to see what's going on here in terms of distribution, how we should use t-value to interpret whether we should accept some sort of hypothesis when we're getting the 2 minutes. So suppose you simply do a random draw from a data set of some observation, and find out that the data you get is very far away from the population mean under a normal distribution. Meaning that it's less likely to be observed by chance. Suppose you're doing random draw. You did not particularly choose the rightmost side of this distribution to draw your data. Meaning that, okay, so perhaps population systematically cluster around the left side of this distribution. Meaning that suppose you're trying to measure human height, and then you find out, okay, Since that the average population height I estimated from a random draw of the population in this particular country are on average taller than war average. But the data generating process, I mean that the way that I gather my data follow a random draw. I do not systematically pick taller population. That perhaps means that okay, that country actually due to genetic reasons that they have a taller population. Because if all these conditions are not violated, it means that okay, it's very unlikely to be observed such high above normal population height by chance. That means that they are more dispersed away from the mean value, so that it should also get a larger t value, and that offers stronger evidence to reject the claim that say overpopulation height across the country are follow the average estimate. This same also can be said of z-score. Only that z-score provide a comparable scale or a t-score is unanimous. Finally, we get to the last part of today's lecture. So, so how useful are they? We use, for example, like the beta coefficient estimate and spin error estimation, t-value, z-score to do any are they useful for any real-world application? Well, you can use that for hypothesis testing on the coefficient. So the most common hypothesis test usually involve comparing the null hypothesis against alternative hypothesis. So, for example, you try to prove that there is a positive association between two variables, and that you would not observe this positive association by chance under normal distribution. I mean, okay, so there is some data point just systematically clustered around the higher end of this particular data, and the distribution does not cover the population mean at 0. Right? So try to use this statistical technique to adjudicate to these two claims. The first is okay, it's null hypothesis. There's really no significant relationship between the two variables. Say, for example, temperature and ice cream set, right? And an alternative hypothesis to evaluate that, okay, there's indeed some relationship between x and y, temperature and ice cream set. So that means, try to rewrite our equation. Okay, if you fail to prove that there is some significant statistical relationship between x1 and y, that means the beta term covers 0. Right? It's probably 0. Or not significantly different from 0. And then there is no relationship. Alternatively, it's not, it does systematically differ from 0. That means there is some relationship. Because if there's no relationship, the relationship is reduced to just the beta 0 and this. But if there's some relationship, then we'll show that. That's the null hypothesis. We can compute since we include one explanatory variable into the equation. So we need to use the t value. We want to compute a t statistic given by this. So we will have a t distribution with -2 degree of freedom loss, right? Because we have the dependent variable and also the explanatory variable, so lost 2 degree of freedom against the null hypothesis that y is true. So we can compute the probability of observing any value equal to t or larger. is the p-value. So how do we interpret the p-value? So we can go back to this picture now. So during summertime, so here's my